to go through some of, not necessarily all, of the chapter review questions in anticipation of the test next class. Number one asked you to write a summary of what you think the important points are for this chapter. Well, yeah, an important point, make sure that you bring your calculator. Number two, then, suppose that a three-sector economy has this particular consumption matrix. They had asked you to draw a weighted diagram for this economy. Well, since we have three sectors, go ahead with A, B, and C. I'm just going to keep moving these things around here. So for sector A, consumes 1/10 of what it produces. So for sector A, we make a nice loop. And again, it said a weighted figure here, so we've got to put in the numbers. From A to B, that's 0.2. A to C, that's 0.3. Keep going. B back to A. That's not the same thing as AB. B back to A. 1/10. B loops around itself. Oh, come on. And again, you can have that going around clockwise or counterclockwise. I'm not picky about that. 0.3, and then B to C. That's another 0.3. Sorry, that's a 0.2. And then C to A. 0.2. C back to B. That's a 0.1. And then C to itself is 0.2. So a rather silly looking graph here. They wanted you to then consider the production matrix P, find the internal consumption matrix product. That's a mouthful. Okay, so again, you create your matrix. Matrix C here is a 3 by 3. Type all of those things in, hit tab one more time, and now I know I'm outside the matrix. And I want to go ahead and control variable, store this as matrix C. So then matrix P should be a 3 by 1, 8, 12, 15. And again, I will save that as our production matrix. And again, it really doesn't matter that those are uppercase, those are lowercase. So they want you to first of all find the internal consumption matrix by taking C times P. Again, with our calculators here. C times P. Now again, you can see the difference there between when I first typed it in, those characters there, lowercase, but it seemed like a regular font, I guess we would call that. because I've saved this value, when I type this in, it's bold. That's how I know, yeah, I'm using the right ones. So then the internal consumption matrix product here, again, this is for A, B, and C. So then what they're asking us to do is find the external demand matrix D, where I need to take P minus this matrix here that I just found. Okay, so let's see how the calculator does with that. Asking it to take matrix P, and then from that, subtract the previous answer. Dun da da dum. Here's our demand matrix. So again, this is matrix D. Again, this is for A, B, and C, whatever sectors those are of the economy. Now, the very next one here asks us to find the production matrix, recalling that the production matrix is equal to the identity matrix, that's what the capital I stands for, minus, here we have matrix C. Once we do that subtraction, then we take the inverse and multiply it by matrix D. Now, before I go any further, this is the demand matrix that was just calculated here. I want to, again, all I did was push control and then variable so that I can store this. So it's telling me, okay, what do you want to store? It automatically takes that previous answer. And again, I want to call that the demand matrix. Okay, that's taken care of. Now remember, when you're creating these matrices, you really don't have to type them in every single time, because option number 3 here, if I'm trying to create the identity matrix that I need, all right, come on, let's behave, 7, 1, and I need option number 3. Again, to get that to match up with matrix C, which is a 3 by 3, I need an identity matrix that's also 3 by 3. In other words, it has a degree of 3. Sorry. And there it is. And again, I want to control variable, store that as matrix I as my identity. Okay, now I think I have everything that I need here. And again, our formula starts off by parentheses. Take that identity matrix that I just created, subtract from that matrix C, close the parentheses. Now again, if I want the inverse, I use my exponent key here, -1. Again, do not use the subtraction button. Doesn't like that hardly at all. And then take that times matrix D. And then hopefully my apologies, I've forgotten the fact that for part C, they changed the demand matrix. Okay, what we actually calculated in part B, I didn't need to save. They came up with a different set of parameters here. So fix that problem. Here's the demand matrix 6, 8, 12. Again, our lovely formula there, taking the identity minus the consumption matrix, then take the inverse, and then multiply that by this demand matrix. And wow, those numbers did not turn out very pretty. So I imagine we could just go ahead and round things off, say, to the nearest tenth and make that reasonable here. Let's say about 18.6, 20.4, and 22.2. All right, for the next part here, number 3. Mike and Britt are playing poker for pennies. Mike's holding a very poor hand, is considering bluffing or not bluffing. Britt can then either call or not call. The playoff matrix for this situation is shown. Over the course of several games in which Mike comes up with a poor hand, what should his strategy be? All right, so again, we're looking for the row minimums from Mike's standpoint. That'll be -10 for this one and -2 for that. So again, of these minimums, we're looking for the maximum. And then from Britt's standpoint, we're looking for the column maximums. So that's -2 here, and that's +10 there. And for the column maximums, we're looking for the minimum value. Oh, would you look at that? This game is strictly determined because the maximin and the minimax are the exact same thing. The saddle point for this matrix is -2. So let's and again, this is a matrix here that's written in terms of the row player, which is Mike. Yeah, he should stop playing. Mike's best strategy is not to bluff. Because again, if this is the saddle point here, his best play is to bluff each time. And he's going to lose 2 pennies every single hand. Mike and Britt soon get bored playing that game. They each draw 2 cards from the deck. Mike draws a 4 of spades and an ace of hearts. Britt draws a 3 of clubs and a 2 of diamonds. Then make a new game where each player will choose 1 card to show. If both cards are the same color, Britt will pay Mike the sum of the face value of the cards in pennies. If the cards are different colors, then Mike will pay Britt the sum of the face value shown. Oh, by the way, for our lovely little game here, an ace is just a 1. Okay? So, we need to write things here. I guess we'll leave Mike as the row player. He can show, again, he has a black card, the 4 of spades, and he has a red card, the ace of hearts. Britt will be the column player, and again, we'll go in that same order here. So if both cards are the same color, well, that would mean, say, black, black. That's a 4 of spades and a 3 of clubs. So that's a total of the sum of the face value of the cards is 7. And Britt would pay Mike. And again, this is written in Mike's standpoint here. So that'd be +7 for Mike. Okay. Again, if they're the same color. Well, the other option here then, same color is red, red, but that's a 2 of diamonds and an ace of hearts. So that would be +3 to Mike. If they're opposite colors, Mike will pay Britt the sum of the face values shown. Okay, So if Mike's decides to show his 4 of spades, and Britt goes with the 2 of diamonds, so we have a black and a red card there. 4 and 2, that's a total of 6. But again, that's what Mike would have to pay to Britt. So from Mike's standpoint, that's a negative. And then the other option here, if Mike chooses his red card, which is an ace of hearts, and Britt chooses the 3 of clubs, that's a total of 4. But again, that's Mike paying to Britt. So again, we'll go through the exact same thing we just talked about here. We want the row minimums. So that'll be -6 here and -4 there. We want the maximum of the minimums, and that would be a -4. For Britt, the column maximums, 7 here and 3 there. And we need the minimum of the row maximums, so that would be a 3. This is not strictly determined, okay? So Mike's best strategy is going to be what? All right, so now we need to do I have this? Yeah, look at that. It's all ready to go. For Mike, we need to set up a system here where, again, he's the row player. We're going to use P for the proportion of times that he decides to show the black card, and 1 minus P for the proportion of times he's going to show the red card. So again, we need to multiply row times column. So we'll have P times 7, that's 7P, plus 1 minus P times -4. So 1 times -4, I guess we can just change that to -4. And -P times -4 is going to be plus 4P. And then this times the second column, P times 6 is -6P. 1 minus P times 3. Well, 1 times 3 will be 3. -P times 1 is -3P. So again, this is going to be the proportion of times for red. This is the proportion of times, I'm sorry, black first, then red. We want to know where he breaks even. All right, so that needs some cleaning up first. 7P and 4P, that would be 11P minus 4 is equal to -6, and -3 is -9P plus 3. Combine like terms now. I'm going to add 9P to both sides. So that'll give me 20. And then variables to the left, constant should go to the right. That means I'm going to add 4 to both sides. Divide by 20. So he's going to show that black card 7 out of 20 times, which then for his red card is going to be the complement there. So that should be 13 out of 20 times. However, for Britt, we go the other way. Now again, in this case, we have to Since Brit is the column player, pick a different variable. I don't like Q. I can use R and 1 minus R. So again, row times column. So 7 times R would be 7R. Negative 6 times 1 minus R. So negative 6 times 1 is going to be negative 6. Negative 6 times negative R plus 6R. And then I take this second row times the column. So that's negative 4 times R is negative 4R. 3 times 1 is 3. 3 times negative R is negative 3R. But again, we're going to just go ahead and set those two elements equal to one another. Combine like terms, 7R and 6R. Negative 4 and negative 3. Let's add 7R to both sides. Well, isn't that interesting that we get the same, we're going to get the same denominator. And then variables go to the left, so that means constants go to the right. A little bit of dividing. For Brit, 9 out of 20 times. Show that black card. And then it's 11 out of 20 times for the red. So for part C, it asked you to come up with a probability tree to find the probability of the 4 different outcomes. And again, if we're going for Mike first, black is 7 out of 20. Red is 13 out of 20. And then for Brit, we have to duplicate these. 9 out of 20 and 11 out of 20. Nine out of 20, 11 out of 20, 9 out of 20, 11 out of 20, and do the lovely multiplications here. Again, common denominator, that just makes it easier. So black, 7 times 9 is 63. 20 times 20 is 400. So then black, red, that's going to be 77 out of 400. Red, black, 13 times 9, that gives us 117, again out of 400. And 11 times 13 for red will be 143 out of 400. And again, a quick check, making sure that all of those give us the sum that we need. Okay, so for our probabilities, I'm just going to copy those down again. 63 out of 400, 77 out of 400, 117, and 143. So then we put, again, from Mike, if both of them are black, he gets 7 pennies. If it's black, red, he has to pay 6. If it's red, black, he has to pay 4. And if it's red, red, he wins 3. So with this lovely chart, we can then find those products and then come up with Mike's expected outcome. So I've just gone ahead and put those in. Again, the losses I just typed in as negatives. Bum, 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 bum. Now, one way to interpret that, if we like our fraction, he's going to lose on average 3 cents for every 20 times they play this. Or if you want the per hand, he's going to lose 0.15, 15 hundredths of a penny for each hand, for each round. Okay, for number 5, the discrete mathematics teacher has 3 class starter activities, one of which she uses to be in class every day: pop quiz, quickie review, and a small group problem solving activity. She never uses the same activity 2 days in a row, which to me is astounding record keeping. Um, if she gives a if she gave a pop quiz yesterday, she's going to toss a coin, and if it comes up heads, then do the review. Again, the implication here is if it comes up tails, then we do the small group problem solving activity. If she used a review last class, she will toss 2 coins and do the problem solving activity there if both of them come up heads. If yesterday was a problem solving activity, then she's going to throw 3 coins in the air, and if all 3 of them come up heads, we're going to take a pop quiz. And again, we have, just so that we didn't have to do it, thank you, authors of the book, here's the transition matrix. So then, if the teacher gives a quiz on Monday, what's the probability that she will give another quiz on Friday? Mind you, that's 4 days later. Now, one thing I'm not sure we've discussed this before. Before I take that lovely transition matrix and start entering that into my calculator, I want to avoid the possibility that from a previous problem, I don't know if I want to call this the transition matrix and use the variable t. I don't want to get it mixed up with something else that I've already used. So, what my preference is, okay, so I've got all of these wonderful things already saved in here. I will, with my Nspire, go back, push that home button, because it's got a little icon that kind of looks like somebody's home. And I will just choose new document. Now, everything in this life is fleeting. Do I want to save it? No, it really wasn't that important that I need to save it to begin with. So, all right, clean slate here. Now I can put in that lovely transition matrix. Okay, so if they're asking, yeah, we took a quiz, which is the first row there on Monday. The probability, another quiz 4 days later, we're simply going to take matrix T and raise it to the 4th power. Oh my goodness. We're looking for this very first element. Okay, so it comes back to there was a quiz, we're taking another quiz, So how about a decimal 147 divided by 512 is approximately 29, if say we round that to the nearest whole number, 29% of the time. In the long run, how often should students expect the teacher to start class with a quiz? How long is long run? Say t to the 20th power, t to the 30th power. Okay, just in case you were not enjoying all of those lovely fractions, look at how long that is. All I did here was the standard change this into a decimal approximation by hitting Control and then Enter. All right, my goodness, that's so much easier to look at. And again, the quiz column then, uh, from a quiz back to a quiz, eventually a third of the time. From the review to a quiz, a third of the time. From the project to a quiz, one third of the time. So there's our answer. About one third of the time, the teacher's going to start class with a quiz. 40% of the time with the review activity, and about 27% of the time with the project. Yay, technology. All right, for number 6, the Super X sells 3 kinds of sandwiches that many of the students at Southeast High especially like for lunch. The Super X Original, the Italian Special, and the Barbecued Beef. The Circle X clerk observed that the same students were coming in for sandwiches every school day. The kind of sandwich that each student purchased depended upon what they'd gotten the day before. So, start keeping track of things, conducted a survey, and found the following. And again, we're supposed to set up the transition matrix in this lovely Markov chain. Okay, so it says students who ordered the original on the last visit, 20% of the time ordered again the next time. So from original to original, 0.2. Whereas 25% switched to the Italian, and then 55% of them to the barbecued beef. Again, quick check, make sure that we have a sum of 1. Students who ordered the Italian sandwich last time, 35% did so again the next time, so careful. Italian is not this first box, it's the middle one. 45% switched the original, and 20% chose the barbecue beef. And then finally, last time we got the barbecue beef, 55%. That's a really good one. I'm going to order it again more than half the time. 20% the original, and 25% the Italian. So here's our lovely transition matrix. And again, it's a Markov chain, again, for many reasons, but again, making sure that you check those row totals should be equal to 1. If the same students tend to buy Super X sandwiches for lunch every day, what's the probability that the student who buys the Italian sandwich on Monday will have it again on Wednesday? Okay, so that means then creating this matrix here and using the power of exponent. So I'm going to say that is S for sandwiches or Super X. Pick your favorite variable. The probability of another Italian sandwich on Wednesday. So from Monday, Tuesday, Wednesday, that's 2 days later. Again, reading our lovely matrix here, the middle row, middle column is Italian this day, Italian that day. So this happens about 28.5% of the time. Then they asked you, in the long run, what do they sell? Okay, what's long run mean? Yeah, that looks like it's pretty much settled down by now, doesn't it? So again, a slight edge there. The Italian is about 27.8. The original only 26.9, but their bestseller is the barbecue beef at 45.2% of the time, which makes you wonder why they don't do something to update the original and make that more appealing. Then again, maybe that's just me. Okay. 7, again, drawing the weighted digraph, the consumption matrix. Those are pretty similar to what we went through already with problem number 2, so I'm not going to repeat that. Number 8, again, we could go through that. Seemed like that was very similar to what we did there in problem number 4. Again, companies are competing for sales at 2 school districts. So what percentage of their time are they going to focus here? What's the best strategy for each company? So P and 1 minus P, and then Q if you prefer, and 1 minus Q as a column matrix. Basically, this is bad news for District B, because it turns out the best strategy for both companies there is to actually focus on District A, and that's that. Suppose that final day's political campaign for mayor, Democrats and Republicans are planning their strategies. Go after those undecided voters. Democrats have decided on 2 strategies. The Republicans counter with 2 strategies of their own. And we're not going to tell the other side. So we're giving the mysterious names Plan A, Plan B, Plan C, Plan D. Following matrices give the payoff for the Democrats. Again, they're the row player in this case. For the various combinations of strategies. The numbers represent the percentage of the undecided voters joining the Democrats in each case. So, again, we're going to go through best strategies and expected payout. Again, that's setting things up there, doing matrix multiplication. Um, Again, very similar to 4. I'm not sure we're going to rehash this here. So the Democrats' best strategy is to go with strategy A 1/4 of the time, B 3/4 of the time. For the Republicans, their best strategy is to go 50-50. Strategy C half of the time and D half the time. The expected payoff for the Democrats is 45% of undecided voters will join them. Okay, if you're looking for a winning strategy here, well, hopefully you've got a bigger base then, because if you're only going to win 45% of the undecided voters, by my calculations, that's less than half. That is not going to turn out well. Um, and again, number 10, we've got the 3 sector, 3 location economy, I guess we could say. Um, and again, that's very similar to earlier ones. Number 11, let's go to that one because that requires a bit of a different approach. So it's not just two strategies from the Democrats and the Republicans, or this is very similar to the pizza wars because this is a 3 by 3 with the two stores competing here. The milk battle, I guess. Following payoff matrix shows percentage of customers who go from store A to store B for each combination of strategies here. Um, Now again, to me, this is phrased rather strangely. The percentage of customers who go from store A to store B for each combination of strategies. So if store A raises their prices and store B also raises their prices, 4% of the people are going to start going, who used to go to store A, are now going to go to B. Store A raises their prices and store B has no change, then percentage of customers who go from store A to store B is -1. I think the way that it's written there in the book is poorly phrased because basically it's the reverse of what these numbers are showing. Okay? Who go from store A to store B for each combination of strategies. I think we should just consider this to be the percentage change. If store A is written as the row player, both stores raise their prices. Evidently, people feel better about store A because, to me, again, the way that the numbers make sense is store A is going to gain 4% in the number of customers. If they raise their prices where store B keeps their prices the same, well, yeah, more people are going to go to store B, but it's only going to be a change of 1%. And yeah, this is not good. If we raise our prices and store B lowers theirs, we're going to lose 4% of store A's customers. No change for store A and store B raises their prices. Well, yeah, seems like we should gain customers. No change is 1. Again, people like us more. No change, store B lowers, yeah, we're going to lose some. If we lower and they raise, oh yeah, that's the best outcome for us. And again, we lower prices, they don't change them at all, we're going to gain. They lower and we lower, yeah, +3. I'm not sure that one is consistent either. So if again you think back to the pizza war problem, that was actually a 4 by 4 rather than this one's just a 3 by 3. But what we need to do here is get it down to a 2 by 2. Then we could go ahead and use our algebra skills there to determine um, best strategies. Okay, so from the perspective of store A, raise, no change, or lower, I think this is just from a business standpoint, this is rather obvious. Um, Raising prices means, depending on what store B does, 2 out of the 3 scenarios, we're losing customers. If we don't change our prices, there's only one scenario where we lose customers. If we lower our prices, everything's a winner. So we're going to say we're going to try and not raise prices. So for store B, yeah, pretty much the same thing. Okay. If we raise our prices, we lose every single time. If we keep them the same, sorry, I kind of drew right through that negative sign there, didn't I? If we don't change and they raise their prices, we're actually going to gain customers. If we don't change the other 2 scenarios there, we lose, but we're not losing as much. And if we in fact lower prices 2 out of the 3 scenarios there, we win. So yeah, let's not raise prices. So now we've got it down to here's our new matrix. We don't have a saddle point here. So again, the process that we looked at earlier there with our lovely algebra, what percentage of the time are they going to keep their prices the same? How much are they going to lower them? And then column matrix there. Turns out, final answer here, for store A, their best bet is to lower their prices. Store B is to keep things the same. All right, I hope that helped. Um, Again, make sure that your battery on the calculator has some charge in it. We'll all be back together on Monday, hopefully in room 202. If not, I'll let you know. So be prepared to do the Chapter 7 test on Monday, and then we'll find something interesting to do on Wednesday to wrap up that week.